Okay. Now, the next case is a pipe with one closed end. Okay. Now, like I mentioned, at a closed end you will always have a node. Okay, and an open end you will always have an antinode, because at the closed end the air particles are being reflected off in a standing wave. So the first mode of vibration will look like this. Okay. Now if you notice, this is 1/4 of a wavelength. Okay, because the entire wavelength would have 3 more parts like that. So if 1/4 of the wavelength is L, lambda in that case is 4L. Okay? And my frequency then becomes V over 4L. Okay? Now, let's see what's the next mode of vibration. The next mode of vibration, again, I need to have a node here and an antinode here. Will look like this. Okay? Now, over here, let's determine what the wavelength is. In order to complete this wave, I need to go up until here. Okay. So, how many parts? Let's divide each node and antinode. I've divided this into 1, 2, and 3 parts. Okay, and I need 4 parts out of that in order to complete one wave. Right. So, my lambda then becomes 4L over 3. Okay, and my frequency here then becomes 3V over 4L. Okay, so notice now that this is 3 times the fundamental frequency. Okay, now 3 times the fundamental frequency means the third harmonic, not the second harmonic, which means that there was no second harmonic for a pipe closed at one end, because at 2 times the fundamental frequency there is no standing wave setup. Okay, this is a restriction that happens because of the one node and one antinode condition. Okay, so therefore there is no second harmonic. We've moved on straight to the third harmonic for a pipe closed at one end. Okay, and this here would be 3 times the F1. It's also called F3. Okay, so as a pattern here, we will notice that there are no even harmonics for a pipe closed at one end. There are only odd harmonics. So the next harmonic then should be the 5th harmonic. Okay? Okay, how do I calculate the wavelength now? Let me divide it again. So I've divided this into 1, 2, 3, 4, 5, 6, 7 parts. Okay, I think there's a mistake here. Let me redraw this. Okay, this would be the next harmonic. Okay, let's divide this now. We have 1, 2, 3, 4, 5 parts, and I need 1, 2, 3, and 4 parts out of 5 of L in order to get this the wavelength. So over here, speed remains the same. Wavelength is 4L by 5. Okay. And my frequency then becomes 5 times V over 4L. Okay, you can notice that this is 5 times the fundamental frequency. Therefore, this is the 5th harmonic. Okay, so after this, we would move on to the next harmonic, which would be the 7th harmonic, 9th harmonic, etc. So for a pipe closed at one end, there are no even harmonics. The general formula in this case becomes lambda n is 4L over n where n equals 1, 3, 5, etc., etc. Okay, and this one becomes nv over 4l, where again n is 1, 3, 5, etc. Okay, so this is these are the three different cases of standing waves which will be tested in the exam, and 11.1.4 is comparing standing waves and traveling waves. We've covered the properties. Firstly, energy is propagated in traveling waves and not in standing waves. The amplitude is the same for all particles in a traveling wave, whereas it's different for standing waves. And the phase difference can be anything between 0 and 2 pi for traveling waves, but for standing waves only 0 or pi. And yeah, that pretty much covers the first part of wave phenomena. Okay, 11.2 is Doppler effect. So let's understand first what is Doppler effect. If we have a source of waves, and this source is emitting waves outwards radially, this is what the wave fronts would look like. Okay, now for an observer over here, okay, this is the source, this is the observer. For an observer here, the wavelengths of the perceived wavelengths of the wave is pretty much the same as what was emitted at the source. Okay, but now in a case when, let's say, the source is moving maybe towards or away from the observer, when the first wave was emitted, the source was here. Okay, the next wave, this one, when it was emitted, the source was probably somewhere here. So the wave should be centered somewhere around here. Okay, the next wave over here, which is the newest wave to be emitted, when that was emitted, the source was somewhere here. So again, the wave would be centered around this. Okay, so roughly you can understand that now the source is over here, and you can see now that the wave fronts have gotten crowded over here. Okay, and they have become more spread out on this end. Okay, so for an observer over here towards which the source is moving, you can see that the wavelengths have become shorter. Okay, so the wavelengths have become shorter here, and the wavelengths have become more spread out for an observer for which the source is moving away. So this would affect the perceived sound. For example, we are talking about sound waves. The perceived wavelength and the pitch of sound would have changed, and this is the effect which causes trains whizzing past or vehicles whizzing past to change the pitch when they actually move past. That's because of the Doppler effect. Now, notice one thing pertinent to the exams. Somewhere along this line over here, okay, slightly behind the source, okay, slightly behind the moving source or the crowding of the wavefronts, along this line, an observer will observe the wavelengths and the frequency at the original pitch. Okay, so somewhere over here, the observer can observe the original wavelength and frequency. Okay, so that's important for exams because there was a question related to that. Okay, in astronomy, okay, what happens now is that over here the frequency gets increased and the frequency gets decreased at the other end. So in astronomy, how this relates to astronomical objects is that when something is moving away from us, their frequency will be decreasing. So something that should be appearing white in color appears towards the red side of the spectrum, as red light has lesser frequency. So something that is appearing red means that it's moving away from the observer, which is us. So that phenomenon is called the red shift, and the opposite would be a blue shift. So a blue shift would mean that the object is moving towards us. And since, because of the red shift phenomenon, we have been able to observe the pattern in which the universe is actually expanding. Okay, now applying the Doppler effect equation for sound. So when, let's say there's a source here and an observer here, okay, and the source is moving with the speed vs, okay, and this is the new position of the source. So now if we have to calculate for a stationary source the wavelength perceived at the observer, now the wavelength would be the distance traveled by the wave divided by the number of waves, okay. So the distance traveled by the wave would be its velocity multiplied by the time difference or the time interval that we're talking about, and the number of waves would be the frequency multiplied by the time interval, okay. So the frequency multiplied by the time interval should give us the number of waves. So distance traveled divided by number of waves should give us the wavelength, okay. So this here is V over F. But now in the moving source, the distance traveled actually changes. It reduces from V delta t. You have to subtract away the speed of the source multiplied by delta t. So this much distance has reduced in the equation now. So this divided by F delta t gives us V minus Vs over F. Okay. So this here is the observed wavelength. Now, if you see the calculation on page 8, this here is the observed wavelength. How does it relate to the, we want to calculate in terms of frequency. So the frequency here, F dash, this should be, okay, F dash will be the velocity divided by the observed wavelength, okay, and therefore lambda dash will be V over F dash, okay. So we can substitute V over F dash over here, okay, we will get V over F dash equals V minus Vs over F, okay. Working this out gives us F dash equals F multiplied by 1 over 1 minus source of the, velocity of the source divided by the speed of sound in air, okay. So this happens when the source is actually moving towards the observer. So you can see that the frequency observed is actually higher than the frequency which was originally let out by the source. Now if the source is moving away from the observer, in this entire calculation we would have a positive sign here, and we would have the final observed frequency to be smaller than the original frequency, okay. So there's a minus sign if the source is moving towards the observer. There's a plus sign if the source is moving away from the observer, okay. This one is for source moving away from observer, okay. So these are the two formulae. The students do not really need to know or like really memorize the formula or the derivation, but what they really need to know is how to apply which formula in which situation, okay. So what they need to understand is source moving towards observer is going to cramp the wavelengths and increase the frequency, therefore the observed frequency should be higher, and in the opposite case the observed frequency should be lower, okay. Now in a separate case for sound, when the observer is moving and the source is stationary. Now let's say the observer is moving towards the source with a speed VO, okay. Now in this case, when the waves hit the observer, the waves are actually appearing towards the observer with a speed V plus VO, okay. So the observed frequency should simply be V plus VO divided by the wavelength, okay. So in this case, in the first case, we should notice that the speed of sound does not change regardless of the speed of the source. But in this case, the observed speed actually changes because of the observer moving towards the source, okay. When the observer is stationary and the source is moving, the observer will still see the waves coming towards him or her at the same speed, which is the speed of sound, okay.